So coming back to our original idea that we want to find the directions of highest spread, of highest variance, and we do that, as I said before, on normalized data. So here is just coming again the justification for that, what I just said. Once we have the normalized data, let's reconsider where we want to go. We want to find the directions of highest variance, and we'll have a look at this right now. So first of all, once again, we do the normalization as typically as we do before, and once again, the reason for that is that the covariance of two normalized features is the same as the correlation of the non-normalized features. You can even prove that if you want. So you can just do this short math here. N is the number of features. The number of observations, not the number of features, of course. N is the number of observations here. So anyway, we will work on the normalized data because we then have just to deal with the covariances rather than the correlations. And once again, the intuition of PCA is more or less the same as we did before with the physics and the statistics grades. So we wanted to look at the different grades and compare among students. Now we want to find the direction of the highest variance, because we hope that in this direction we have the highest chances to discriminate between patterns. So that is the basic assumption of PCA, that the feature or the directions of highest variance are the best candidates to find some patterns in the data, and not the low variance directions, obviously. We will see that this need not necessarily be the case. So be clear that, again, PCA assumes something, and if the assumption is not true, then PCA is probably not a good idea to apply. Just that you know. So PCA is not a one-fits-all solution for unsupervised features reduction or feature selection, just that you know. So once again, the intuition as before, more or less, we have a data set. X2 and X1 are the features, and we see here that feature X2 has a considerably lower variance than X1. So if we want to reduce the features, we would probably, in this assumption that the feature with the highest variance or with high variance are better suited for comparing among the observations and for finding patterns among the observations, we would certainly keep X1 and delete X2. So we could delete X2 or disregard X2 by just projecting everything on X1, which would result in this one here. And then hopefully, in just looking at X1, we will find some patterns in the data. So that is a little bit awkward here and arbitrary, because here we have a kind of normal, equal distribution. Same here, obviously. But that's the basic idea. And of course, if the features, these original features, are correlated, so that is the same example as before with the physics and the statistics grade in the correlated case. So if these features are correlated, and maybe also have similar variances, we don't know exactly should we use X2 or X1, because they have more or less the same. Well, not really here, it's a little bit squeezed here, but let's consider they have more or less the similar variances. So in that case, none of those two features give us really some kind of clear winner in terms of highest variance. So in that case, we try to find new orthogonal axes, like the direction of highest spread, of highest variance, PC1 here, and PC2, which is orthogonal to PC1. And PC1 obviously explains the most of the variation. And if we rotate the points now, so if we take PC1 and PC2 as new features, as new basis vectors for new feature space, which we could do because they are orthogonal to each other. So PCA gives us orthogonal principal components. So if we do that, if we rotate that, looks like this one here, then we can keep or project everything to PC1 and omit PC2. Yeah? And then we have again a reduced feature space from 2 features to just 1 feature. The new feature is now PC1. It's not is a linear combination of x1 and x2, the original features, but not one of the original pure features, so to say. Yeah? So that is the basic idea of PCA. We try to find the directions of highest variance and then rotate the data and project it on those principal components, on those directions of highest variance, in order to reduce the feature space. The good thing is that PCA actually finds the optimal rotation such that the transformed data explains the complete variability of the data. Yeah. So if we don't omit anything, PC1 and so if we keep PC1 and PC2, the whole spread, the whole variance of the data, of the original data, is kept, actually is saved. Yeah. So that is the first good idea, good message, so to say. Yeah, because meaning that if we just rotate it like here and don't project it, we still keep the entire information. We don't lose any variation. We don't lose any spread. And the second thing is, since the first K principal components, well, the principal components are sorted according to decreasing variability, decreasing variance. So meaning that the first principal axis, the first principal component, gives us the direction with the highest spread, the second one with the second highest spread, the third one with the third highest spread, and so on and so on. I think it's written down here. Yeah. So the variance along the new axis are the principal components, also called eigenvectors, because PCA is an eigendecomposition in a mathematical sense. Yeah. So for a d-dimensional data set, we get always d principal axis. Yeah. Here in the 2-dimensional data set, we get 2 principal axes, and just rotating the points such that we have a new axis, so that PC1 and PC2 are now axis parallel, like here, and not reducing anything, yields us no information lost. Yeah. So now the variance along each eigenvector, called eigenvalue, because those are the eigenvectors here, yeah, and the variance are called the eigenvalues, is decreasing. So the first eigenvector has the highest eigenvalue, while that should read d here, the dth eigenvector has the smallest eigenvalue. Yeah, so the smallest spread. So in other words, the first component, once again, the first component has the highest spread, the second component has the second highest spread, the third component the third highest spread, and so on and so on. The dth component, since we get always d for d-dimensional data set, d components, the dth component will have the smallest spread, the smallest variance. Now, this can be used, of course, this specific property can be used for dimensionality reduction, where we minimize the loss of spread, the loss of variance, because if we pick the kth first eigenvectors as new axis, yeah, then this transformation from a d-dimensional data set onto a k-dimensional space is optimal with respect to the loss of variance, yeah, because we are sure that by omitting the d minus k eigenvectors with the lowest variance, we optimize the loss. Yeah? So we get the smallest loss of total variance by doing that. So that is the basic idea of PCA, and that is why PCA is good if the assumption holds that the spread, the variance, the high variance directions are the important ones. If this is not the case, then we are lost. Then we are screwed. Then this is not a good method. Yeah? But mathematically, if we don't know anything about the data and think that the variance is important, the variance of the data, then PCA gives us the best possible way, the optimal transformation in a k-dimensional space with respect to the loss in variance, in total variance. Yeah? So that is the key idea of PCA.